In this video, I would like to introduce our primary statistics for analyzing the variation or the spread in a data set. And these statistics are very important so that we can get the full story on our data. Let's take this example here of the bi-monthly average high temperatures in St. Louis and San Francisco. So as you can see, the mean of these bi-monthly average high temperatures in St. Louis is 66.8 and the median is 67. And the mean of these bi-monthly average high temperatures in San Francisco is 64.3 with a median of 64. So if you are just looking at means and medians to summarize your data, then you might walk away from this example thinking that the weather in St. Louis is very similar to the weather in San Francisco. But as many of you know, that's not the case, and we can also see that by looking at the big spread in the data in St. Louis versus a much smaller spread in the data in San Francisco. So let's talk about the statistics that we'll use in this class to describe that variation or that spread in the data. The first one of those statistics is called the range. And the range is simply the difference between the largest value in a data set and the smallest value. So if you're looking at the St. Louis data, you could see that the largest number is 90 and the smallest number is 40. So our range would simply be 90 minus 40, or 50 degrees. We have a 50-degree swing throughout the year in St. Louis. And then if you look at the range in San Francisco, we have a high of 71 and a low data point of 58. And so the range would simply be 71 minus 58, or 13 degrees. And then what you could do is you could say, okay, well, I've got a range of 13 and I can compare that with a range of 50. And based upon the big difference in those ranges, you could justify that there's much more variation, much more spread in the St. Louis data set than there is in the San Francisco one. Okay, let's take a look at another statistic now. It's a little bit more complicated, but it's still going to measure that variation, that spread in the data. This one's called population variance. And population variance is a measure of how far your data values are from the mean on average. More specifically, population variance is an average of the squared distances that data values are from the mean. And so here is the symbolism that we'll use when we're describing a population variance. This symbol is known as sigma. So we say that a population variance is sigma squared. And we use this formula to calculate the population variance. But this formula is quite literally doing exactly what these words say right here. This formula is taking the average of the squared distances that data values are from the mean. I'll show you. So x represents a data point. So if you do x minus mu, you're getting the distance that that data point is from the mean. If you square that, you're getting a squared distance. And then this symbol means sum. Take the sum of all of the squared distances. And then after you have the sum of all of your squared distances, you divide by the number of data points that you have. And so that is the idea of computing an average of those squared distances. So in this class, you will not have to apply this formula. You'll be doing this in your graphing calculator, and I'll show you that in some coming videos. But right now, I want to walk you through just the initial setup of this, just so that you see it one time, and you know that this is what's going on behind the scenes in the calculator. So with the St. Louis data, let's set this up. It would begin with the data point of 40, and we would say, let's look at the difference between 40 and the mean of 66.8. And then we want to square that difference, or that distance. And then let's add that to the next squared distance. So we would have 56 minus 66.8 squared. And then this would continue until your final squared distance of 57 minus 66.8 squared. And then what we would do is we would take those squared distances and we would divide by the number of data points that we had, which was 6. And I'm just going to tell you what this calculation ends up as, and it is 295.8056 if you're going to 4 decimal places. And again, let's denote this with the symbolism sigma squared. So sigma squared, our population variance, is 295.8056 for the St. Louis data. Now let's do the same thing for the San Francisco data. It would be, to start, 58 minus 64.3 squared plus the next data point minus 64.3 squared, and that sum of squared distances continues until we end up with the last data point minus 64.3 squared, and we take those squared distances and we divide by 6. Sigma squared in this case is equal to 16.2222, and that's if you're going to 4 decimal places. So now you could look at this number, this 16.2222, and you can compare it with 295.8056. And just like we did with the range, where you would say, wow, the range of St. Louis is much greater than the range of San Francisco, we could say the population variance for St. Louis is much greater than the population variance for San Francisco, suggesting that there's much greater variation, much greater spread in the data in St. Louis. Now, population variance is a very commonly used statistic, but one of the reasons we use population variance is because it leads to another more common statistic, especially in this class, called population standard deviation. Now, population standard deviation is quite literally the square root of the variance. And so if we're taking the square root of sigma squared, then that means the population standard deviation is going to be simply sigma. And let's go ahead and punch this into the calculator, where we take the square root of 295.8056. Let's see what we get. So square root of 295.8056 leads to 17.19. Looks like that's going to be 90 for rounding to 4 decimal places. So our population standard deviation would be this for the St. Louis data. And then for the San Francisco data, let's do the square root of 16.2222. And we press enter, and we get a population standard deviation of 4.0277, again, if we're going to 4 decimal places. And once again, we can say, let's compare this standard deviation with this standard deviation, and it allows us to draw the same conclusions that we drew when we were comparing variances and when we were comparing ranges. We're seeing that the variation or the spread in the data is much greater for the St. Louis data than it is for the San Francisco data. But population standard deviation is particularly handy for a couple of reasons that variance isn't. And one of those is when we work with variance, look back at this calculation. When you take the difference between a data point and the mean, that's giving you a difference in temperature. So this represents so many degrees. And then you're squaring that. So you're turning your problem into a problem where the units involve squared degrees. Yet when you do a square root of that, then that means that you're converting the units in the problem back to the original units of the data. And so that's very helpful. Additionally, there are some properties involving standard deviation that you'll see in the coming videos. One of them is called the empirical rule. Another one is Chebyshev's inequality. And these are going to have very major implications for us throughout the rest of the course. One of the big ideas involved with the empirical rule and Chebyshev's inequality is the fact that most of your data in any data set is going to be within a couple of standard deviations of the mean. And just to kind of give you a glimpse of what that's like, take a look at the St. Louis standard deviation. So we would say that one standard deviation in the St. Louis data set was 17.1990. Let's just round and say it's about 17. So if one standard deviation would be 17, then 2 standard deviations would be 34. And so one of the big ideas that you'll see is that the majority of our data should be within 2 standard deviations of the mean. And so if we go back to the original St. Louis data and we take a look at it, let's see if these numbers are all within a couple of standard deviations of the mean. Well, I think that's going to happen because a couple of standard deviations, remember we said, would be about 34. So if you went 34 on either side of the mean, that's going to take you all the way down to about 32 degrees, and it's going to take you all the way up to almost 100 degrees, or right around 100 degrees. So yes, all of these data points are within a couple of standard deviations of the mean. Now, with the San Francisco data, the standard deviation was approximately 4. So 2 standard deviations would be somewhere around 8. Now, that would suggest, if we're thinking about this idea that you're going to see in a little bit, that the majority of our San Francisco data should be within about 8 of the mean or so. And so if you go 8 away from the mean on either side of 64.3, you'll go up to 72, you'll go down to 56. And yes, all of our data points are within 8 of the mean. All of our data points are within a couple of standard deviations of the mean. And it's not always going to be the case where all of your data will be within a couple of standard deviations of the mean, but you'll see when we discuss the empirical rule and Chebyshev's inequality in detail that the vast majority of your data will be within a couple of standard deviations of the mean. And so we'll dig into those ideas a little bit in the coming videos. But to end this video, I want to introduce one final idea. And that is, sometimes we're not interested in working with population variances and population standard deviations. Sometimes we're actually going to be interested in working with sample variances and sample standard deviations. Now, a sample variance is a little bit different than a population variance in terms of how it is calculated. If you take a look at this formula right here, you could see that we're dividing by n-1 instead of dividing by n. Also note that I'm using a different symbol. Population variance we said was sigma squared. Sample variance is s squared. Now it's a little bit difficult to explain why we're dividing by n-1 when calculating a sample variance compared to a population variance, but there is a link in your notes, and I strongly encourage you to click on that link and go watch that short Khan Academy video that gives an informal explanation as to why we need this type of a correction when we're using or calculating a sample variance. So you can check that out, and if there's a sample variance, then you'll also have a sample standard deviation. And the sample standard deviation is going to have the symbol just S. So we have to try to keep these things organized and pay close attention to what we're going to be asked for, because you will get slightly different answers for your sample variances and sample standard deviations when compared to the population variances and population standard deviations. So the final thing that I'll do here, I'd like to summarize the different statistics and parameters that you've seen so far in this module. So let's just note these as some parameters and their corresponding statistics. So we have observed mu as a parameter, and its corresponding statistic was x bar. We've observed sigma squared now, and sigma. That's population variance and population standard deviation, and its corresponding statistic would be s squared and then s. And try to remember that statistics are always reflecting what's happening in a sample, whereas parameters are always reflecting what's happening in a population. We'll continue to use these symbols and this vocabulary throughout the remainder of the class, so it's definitely really important to master it right now. Okay, so now I suggest checking out the next video where I introduce an interesting application of a lot of the stats that you've seen here. And then the video after that will actually get into how you'll be responsible for calculating variances and standard deviations in this class. So be sure to check that one out too. Thanks.